In this lesson, we're going to officially, formally introduce the self-inductance parameter L. We are going to see why it makes sense conceptually. We're going to see why it makes sense mathematically. We are going to reformulate Faraday's law in terms of this self-inductance parameter L. So we are going to should have a complete understanding of what this L parameter is all about. So let's get started. The first thing we need to acknowledge, we need to understand, is that the magnetic field, B, is going to be directly proportional to the current I for any differential current element that exists anywhere. So if the current is doubled, the B field that current produces at a point in space is doubled based on the Biot-Savart law. So we have what I am going to refer to as equation 1. So B is proportional to I. We know from the definition of flux that flux is field dot dA. So for the magnetic flux, it is going to be integral B dot dA, so that the flux through any area, as we've seen, is going to be directly proportional to the B field through that area. I'm going to call that equation 2. So this is logic 101. If B is proportional to I and flux is proportional to B, then flux is directly proportional to I. So that is logic 101 to get the relationship that the magnetic flux will be directly proportional to I for a single coil loop. And if we have more than one loop, then we add the N to this equation. So it's capital N, the number of loops, the number of turns of a coil, is directly proportional to I. And then our direct proportionality becomes an equality when we have a proportionality constant. So L, as I have highlighted here, so if you have a highlighter, you can take it out, take your highlighter out and highlight. L is the proportionality constant between the flux and the current through a coil. So it is a constant. And constant is going to be the key term. Remember capacitance. So I know we talked about this in our last lesson, but let's just make sure that we are really focused on the logic approach that we are taking. Because at this point, I think we're comfortable enough with capacitors and capacitance to readily recall that the charge on the capacitor is directly proportional to the voltage across the capacitor plates. So the buildup of charge creates the voltage. It is directly proportional, and capacitance is our proportionality constant, and it was constant. Remember, capacitance for the parallel plate capacitor was kappa epsilon naught A over D. So it is constant. Once the material, kappa, between the plates is determined, epsilon naught is constant. That area of the plates is fixed by the geometry of the plates, and the D is also fixed. The C is fixed. So Q can change, V can change, but C only changes if we literally, actually change out the capacitor. L is going to be the same. Flux can change, current can change, but L can only change if we swap out the inductor or the solenoid. So a solenoid slash inductor. It's the same. So the words are used interchangeably. And we're going to see the derivation for that equation, like we have kappa epsilon naught A over D here. We'll have an equation that describes the inductance parameter L for the solenoid. So we rearrange our equation to get the self-inductance parameter. L equals N magnetic flux divided by current. So it is a strength parameter. It describes the amount of flux per amp seen through a coil or many coils of a solenoid. So if we have a lot of flux, so big flux number, and a small amperage, that means you have a really strong solenoid. So we'll talk more about that. And please, again, make sure you get all of your annotations into your notes. Don't take shortcuts on the annotations. When you look back at the notes as time goes by, the annotations will be important. So L is the amount of flux per amp. It is a strength parameter. My explosive statements here are explosive for a reason. L is constant. Flux and I can change, but L for a given solenoid remains constant, and we're going to do the derivation of that in coming lessons. But for right now, we just needed to get a firm grasp on our proportionality constant. Let me erase my little additions here. Please make sure you get down all of these annotations, and in our next lesson, we're going to introduce a version of Faraday's law with the self-inductance parameter.